In this video, I will talk about how to exploit a Stack Overflow vulnerability with ROP, Return-Oriented Programming. In our last video, we talked about defense mechanisms, and we talked about 3 different kinds of defenses. They are stack canary, SLR, and W XOR X. Question is, can we still be able to exploit a Stack Overflow vulnerability given these 3 defense mechanisms? Let's think about this together. First of all, we know that we cannot execute shellcode anymore because shellcode will be stored in stack, and stack will be set with the flag of non-executable. However, the code that's originally in the binary will still be able to execute it because the binary will need to execute the code. They cannot be set as non-executable. Can we really use those codes that are originally in the binary and make it execute what we want? This is exactly the idea of ROP, Return-Oriented Programming, which is to overwrite the return RIP to point to somewhere in the code segment that will execute what we need and fulfill our malicious intention. In fact, if we check the memory related to a binary, we found that there are a lot of code segments. So if you are using PondDBG or Jeff, and when you debug a binary, you can type vmmap to get the virtual memory mapping information. Here, code is represented in color of red, and you see that there are indeed a lot of segments that are executable and can be reused by us if we are the attacker that know how to use ROP. However, we also know that it's very unlikely that there is a sequence that is doing exactly what we want. And this is exactly the case that we want to have shellcode. In last week's lab, there is a record function that is provided in the binary. However, it's very, very unlikely that there exists a sequence of code that is equivalent to function record if function record is not pre-coded into the program. And here comes the idea of ROP chain, which is to cut code into smaller pieces and then chain them up. Recall that in last week we talked about the stack before and after return instruction. So return is equivalent to pop RIP and then jump to RIP. So that means that when the return instruction is invoked, it will first pop the value from the stack and then put that value into register RIP. And then it will jump to the place that RIP is pointing to and then execute over there. ROP chain uses this feature of RET. And this is exactly the reason why it's called return-oriented programming. If we put 2 returns together, then the layout of the stack will be saved RBP followed by 2 saved RIP addresses. So after the first return is called, the first saved RIP will be popped up to RIP, and then RSP, which is the bottom of the stack, will point to the location that is next to the current saved RIP. And then, when the return instruction is called again, RSP will be popped up again, and then the next value will be assigned to RIP again. So the value that is stored next to the saved RIP, which I call it saved RIP2, will be the next return address if we do 2 return together. Following this idea, if we make the first saved RIP points to a location that it has some operation, but it ended with a return, then after those operations such as a move statement, it will then pop up the return address from stack and then move it to RIP again. And if the second RIP address points to the function that we're interested in, that will be able to chain these two places of code together, and we call this a ROP chain. In a ROP chain, each component that are connected with the other is called a ROP gadget. Now I'm going to show you another more complicated example. Let's think about how to come up with a chain and also how to overwrite the stack in order to call system call of execve bin sh. So the system call of execve is composed of two steps. The first step is to assign argument with the correct value. As execve is a system call, it needs to set the RAX, which is the signal of the system call. And in this case, it's equal to hex3b. For the other arguments, we need to comply with the x86-64 calling convention, which we need to put the address of string /bin/sh to register RDI, 0 to RSI, and 0 to RDX. The next step is to call syscall, which is int ATH. We can construct the chain on stack in the following way. So after the saved RBP, the first saved return address will be overwritten to the location that we'll call poprax. When poprax will be invoked, it will pop the value from the stack, so RSP will move higher, and then the value of hex3b will be copy-pasted to RAX. After that, it will return, and then RSP will move higher again. After return instruction, stack will be popped up again, and here we're going to put the value that we preset before, which is the address of another gadget. In this case, the gadget will do pop RDI, and followed by that, we're going to put the address of /bin/h in the stack. So after executing pop RDI, the address of the string will be copy-pasted to register RDI. And similarly, we can continue executing to the next gadget, which will move RSI to 0, and another one which will move RDX to 0. In the end, we will jump to the gadget that will invoke system call, and by the time that the system call is invoked, those registers will have been assigned with the proper value. There are tools that can support us finding the address of those gadgets. For example, you could use ROP gadget or ROPium. These two tools are very useful, and you can just download it from GitHub and play it by yourself. And ROP can be very creative. Right here, I'm just showing one example, and there are much more ways to create a ROP chain. If you're interested in ROP challenges, I encourage you to play some ROP challenges from CTF games. And of course, in our lab, we will also have ROP challenges for you to play and have fun with. Due to the fact that ROP is challenging, I'm not going to show you a demo in this video. Instead, I will show you how to play with ROP in an in-class lab. See you over there.